we know how important performance is for our developers. Rendering high-quality content at the resolution and frame rate that is required for a smooth VR experience is extremely challenging. This is why our teams at Meta focus a lot of time and effort into application performance so that developers can build the best VR applications for Meta Quest devices. Hey everyone, I'm Luc Charbonneau, a software engineer on the developer architecture team. And today, we'll talk about some of the performance optimizations that we've been working on in the last year. We'll present to you a new feature that we're really excited for our devs to get their hands on, eye-tracked foveated rendering, or ETFR, coming on our new Meta Quest Pro headset. We'll discuss symmetric FOV and give a quick update on application space warp that we introduced last year. We'll also go over some of the memory optimizations that we shipped for Unity Vulcan. And finally, Jimmy will present an update on some of the valuable tools that developers use for maximizing the potential of their applications. This includes some improvement to Perfetto, as well as RenderDoc Metafork, formerly known as RenderDoc for Oculus. But before we get to Jimmy, I'll hand it off to Ross, who's going to do a deep dive into our latest optimization, eye-tracked foveated rendering.
Hi everyone, I'm Ross Ning from the WebXR mobile graphics team. I've been working on bringing new graphics features to VR for the past 4 years. You are probably familiar with FFR, or fixed foveated rendering, which renders full resolution in the center of the screen, often called the fovea region, and low resolution in the periphery. This provides substantial GPU saving for Meta Quest applications. Now with eye-tracked foveated rendering, or ETFR, we're pushing the boundary forward by moving the fovea region around to match where you're looking using eye tracking. Because the low-resolution region is always hidden in your peripheral vision, we can now use more aggressive foveation maps, hence delivering more GPU saving. So here is how ETFR works at a very high level. First, we have the user's gaze computed from eye camera images. We then use the gaze information to move the high-resolution region around. In order to do this, we're using the new Vulcan extension from Qualcomm called Tile Offset. With this extension, we can reuse the same foveation map, but simply move it around at much finer control. This avoids the flickering artifact in the traditional method, where we change the pixel density for each tile individually. In our ETFR pipeline, the camera sensors and the processing are fully synced to the rendering pipeline in order to minimize the latency between eye movement and the display time. The end-to-end latency measured in our UE4 application is roughly 46 to 57 milliseconds. Along with eye tracking gaze prediction, we're able to get a very good visual experience for all kinds of eye movement. One of the major benefits from ETFR is GPU saving. For example, the following diagram shows a perf comparison between FFR and ETFR in a UE4 test application. As you can see across all foveation levels, ETFR provides better GPU saving than FFR by using the more aggressive foveation map. But it's also important to note, perf and quality are always trade-offs. As a game developer, you are responsible for choosing the foveation level that best fits your content. We recommend to start at the lowest ETFR level and increase until you start to see some artifact in the periphery. One simple way to use the extra GPU saving is to increase the render target size, which improves the graphics quality in the fovea region creating sharper and crispier images. Here is an example of what we measured in our UE4 test application. Let's say, if you were rendering with no foveation, default resolution, and MSA4, you might want to try ETFR level 1 at higher resolution, MSA2, which renders at similar GPU time but gives better image quality. Similarly, if you were rendering at FFR level 3, MSA4, you might want to try ETFR level 2 with MSA2. The GPU saving you'll get from ETFR will depend on your application's content, so make sure to profile your application at different foveation levels and render target size in order to determine which combination works the best for you. On the other hand, increasing the render target size isn't the only way to use the extra GPU saving. It's up to you to decide what to do with it. With ETFR, we also recommend turning on subsample layout for your application. This enables bilinear upsampling from low-resolution regions, removing pixelated artifact in your periphery. Now I'll pass it over to Luke, who will cover the engine integration for ETFR.
There are a few things to keep in mind while integrating eye-track foveated rendering in your application. Since some users might prefer the look of FFR over ETFR, it's a good idea to have an option for it in your application setting so that users can toggle it. It's also important to mention that some users might disable eye tracking entirely. In that case, ETFR will be disabled accordingly. And finally, since the eye tracking sensors are only available for the Meta Quest Pro headset, ETFR will only work on that device. You'll want to make sure that the device supports the feature before trying to enable it. With these three considerations, it's important to understand that whatever you decide to do with the extra performance gains might need to be disabled when eye-tracked foveated rendering is turned off. ETFR is really simple to integrate into your Unity or Unreal application, and our developer documentation has all the details. ETFR will be available in our V46 SDK for both Unity and Unreal Engine 4 and 5. Another feature we want to mention is symmetric field of view, or symmetric FOV. In the past, on MetaQuest, applications would render using asymmetric FOV to prevent rendering areas that are not visible through the lenses. By switching back to symmetric FOV, we're actually rendering a bit more than what's visible to the users, but we have two optimizations that makes it more performant than its predecessor. First, by using multi-view, which renders both the left and the right eye tiles at the same time, there's a higher chance that the content will be similar in both eyes when symmetric FOV is enabled. This results in a better cache coherency, which results in a better performance. The other optimization we do with the help of the fragment density map extension is to turn off rendering for tiles that are invisible to the users. You can see what it looks like here. The gains you'll get from symmetric FOV might vary depending on a few factors like IPD and even foveation levels. You might also see more gains when using complex vertex shaders and less in the cases where your application is fragment bound. Symmetric FOV is on by default for Unreal applications, and Unity devs can simply enable it in the Oculus XR plugin settings. Last year, at Connect 2021, we launched Application Space Warp, which can give you back up to 70% of CPU and GPU time. At a high level, what Application Space Warp does is synthesize every other frame for your application from the information of the previous frame. You render your app at half the targeted frame rate, so if you're aiming for 72 FPS, you'll render at 36. In addition to the eye buffer, you'll also need to render a motion vector buffer and a depth buffer. And with that information, our system is able to generate the next frame for you. Developer adoption of Application Space Warp has been fantastic, and we continue to improve the tech based on your feedback. We're currently working on some showcases so that developers can easily see how good application space warp looks and how to make the best use of the feature. And finally, let me tell you how we've been improving memory for applications using Vulcan in Unity. About a year ago, we noticed that using Vulcan for some applications resulted in much more memory usage than when using GLES. After months of efforts, we're happy to announce that we've made huge memory wins on Vulcan. In fact, our optimization saved over 1 gig of memory for one of our AAA developer projects. We think most Vulkan Unity applications will benefit to some extent from these optimizations. Be sure to be on the latest Unity 2021 LTS version to benefit from those savings. With all the graphic optimizations we've made in the last couple of years, like eye-tracked foveated rendering, symmetric FOV, and application space warp, we believe that Vulkan is becoming the graphic API developers should be using when developing for our platforms. And with the huge memory optimizations that we've shipped recently in Unity, we're making it easier for developers to make the switch to Vulkan. I'll now hand it off to my colleague Jimmy, who will go through some updates on the tools that will help you tweak your application's performance to its best.
Before working at Meta on VR developer tools, I worked in the video game industry on AAA titles for 11 years. Hi everybody, I'm Jimmy Lee, and I'm here to tell you about the latest performance tools for the MetaQuest platform. My team's goal is to improve VR development workflows and tools with an emphasis on high-quality video game production. Today, I'll be showing some of the new tool changes that will be coming your way very soon. You might already be familiar with some of these tools, but I'm going to demonstrate some new tricks you can perform to get deeper access and more information from your device. We introduced the Performance Interface Library, or PIL, 2 years ago. PIL grants some of the most popular tools on our platform, such as OVR GPU Profiler, RenderDoc Metafork, and Perfetto, the ability to perform GPU traces. A GPU trace captures detailed, low-level information on the work your application sends to the GPU. And it can reveal performance inefficiencies or bottlenecks. PIL currently offers 3 different types of traces. First, real-time monitor that gives a global view of the system metrics. Second, render stage trace surfaces low-level information related to the different stages of the mobile GPU pipeline. Render stage trace can also operate in low overhead mode, which reduces performance overhead by omitting some parts of the trace data. And finally, draw call trace that pulls low-level hardware counters while disabling hardware concurrency in order to report per draw call metrics. Available in V46, applications will no longer need to declare internet permission in order to participate in a GPU trace. Furthermore, you will be able to see the Oculus VR runtime service among other services in the GPU trace as well. Let's take a look at how to do this using Perfetto. Before launching your app, enter the following ADB commands in a shell. ADB shell OVR GPU Profiler -E will put the device in detailed profiling mode. Then, we will use 2 ADB force-stop commands to stop 2 system services. When a system service is stopped, it'll restart on its own. Then, simply launch your application and record using the new data source shown here. The change of data source is necessary in order to handle large amounts of GPU data. The change also improved the GPU track UI dramatically, making it much easier to read. Now, if you already have tools set up to record GPU trace through a track event configuration, there is no need to update because track event GPU trace will continue to work. And the improvements are retroactive so that you can enjoy the UI improvements and system service participation using track event configurations as well. In just a moment, we're going to show you what a GPU trace with system service participation looks like. But before we do that, let's also take a look at the Perfetto one-button trace from Oculus Developer Hub, or ODH. We have made significant performance improvements to ODH, and it'll really help simplify your Perfetto workflow. Let's perform a Perfetto GPU trace using ODH. First, we need to enter these ADB commands before launching your app. Then, launch your app. After entering the ADB commands, open ODH and navigate to the Performance Analyzer. Click on the ellipsis and select Perfetto Settings to set the Perfetto trace configuration. This opens up the trace configuration window. We have made changes to allow your Perfetto trace to allocate a dedicated amount of memory for the purpose of GPU tracing. This is important for the reliability of your trace, as GPU traces can consume large amounts of memory, and that can lead to data loss on other data sources for your Perfetto trace. With the trace configuration window handling the setup, there is no need to study the Perfetto syntax. You can simply toggle GPU render state trace to enable GPU tracing. You can also toggle high precision GPU render stage tracing. Doing so will tell Perfetto to gather more information at the expense of profiling overhead. Click Save to save the configuration. With the configuration saved, click on Record to start the trace. The default configuration will perform a trace for 5 seconds. Once the trace finishes, ODH will automatically open the capture in the browser. You notice that the GPU tracks are now placed at the top. The GPU tracks also show the owner process in parentheses. To enable Perfetto instrumentation in Unreal or Unity, make a debug or development build of your project. You get detailed thread execution from your application shown as a collection of thread tracks, grouped under a process track. You can use the star icon to pin the GPU and thread tracks to the top. That way, you can clearly see the execution dynamics of your app on the device. Let's zoom into the GPU tracks and look at how this app interacts with VR runtime and Guardian service. Here's one frame worth of rendering, and we can see that there is a preemption during the execution of one of the bins. With the GPU tracks placed adjacent to each other, we can now see that this GPU work was preempted for the execution of the VR runtime. Looking over to the thread tracks, we can see how one frame starts from Unreal's game thread, and then the render thread takes over. Then the GPU work begins. While this is happening, the time warp thread from VR runtime performs work on the left and right eye. This results in 2 GPU preemptions you see on the application. Finally, when the application's GPU work finishes rendering, the fence checker releases the lock so the next frame can begin. The entire journey is also visible over here in the CPU core section. This section shows the physical core allocation of threads from all processes. We can see that the render thread here is executing on CPU core 4, and after a short while, continues execution on CPU core 5. CPU 0 to 3 represents the silver cores. CPU 7 is the gold prime or platinum core. And they are reserved for our system softwares in order to produce a judder-free view for VR. CPU 4 to 6 are the gold cores, and your app has full access to them. By inspecting how your app executes with other processes and services, you will gain a deeper understanding of our platform and make more accurate diagnosis. Now, let's look at a tool that works very differently from Perfetto. Instead of instrumenting the app with profile markers, which can result in performance overhead, Simpleperf relies on the performance monitor unit that monitors performance events on the processor. When an event triggers, Simpleperf samples the program counter and looks up the executing function. By randomly sampling over some periods of time, performance overhead can be limited to an acceptable level. The accumulation of random samples forms a histogram of function calls, which can then be used to calculate the event frequency of all function calls from the app. Available now through the Android NDK, we can use Simpleperf to perform sample-based profiling. Under your NDK directory, there is a folder called Simpleperf, which contains a number of Python scripts. While your app is running, use the app profiler command to initiate the sampling. You need to specify the package name of the APK you want to sample. Simpleperf will only sample the hardware event CPU cycles by default. If you want to sample different types of events, you can specify the sampling event types via -e. By sampling different types of hardware events, you might discover different inefficiencies in your app. After the sampling is done, run the report HTML command to generate an HTML file containing the reports of the sampling session. The command will also open the report in the browser when it's done. A Simpleperf report can show us the distribution of time spent in the form of a pie chart based on the events that we sampled. The time spent can be sorted by process, threads, libraries, or functions. To see function names, Simpleperf will need to have access to symbols for the sample functions. The report can also display a function flame graph for each thread. The most expensive functions are stacked at the bottom. Please keep in mind that sampling-based profilers need to take large amounts of samples over multiple frames. As such, it is not suitable for investigating sudden performance spikes within a few frames. Besides the function call statistics we get from Simpleperf, we can now also get shader statistics thanks to our collaboration with Qualcomm. Available now through the Vulcan extension, Pipeline Executable Properties, you get 19 counters to help you optimize your Vulcan shaders. Nobody likes to write extra code, and you don't have to with RenderDoc, since it implements the Vulcan extension right in the shader module panel. With the 19 counters we've got, you'll be able to figure out how your shader is doing. Now, let's take a look at how to access these shader stats in RenderDoc. First, open your RenderDoc capture. In the event browser, navigate to the draw call you are interested in. With the draw call selected, check out the pipeline state panel. Click on the vertex shader stage, and then click on View. In the disassembly type drop-down list, select Pipeline Executable Properties. We will then be shown shader stats for the vertex shader of the draw call. Similarly, if we do the same thing on the fragment shader stage, we will get shader stats for the fragment shader of the draw call. We can also do the same on compute shaders as well. We can see here what the shader stats look like from RenderDoc. A smaller count value generally correlates with better performance, but the optimal value will depend on your artistic vision and aesthetic goals. For more information on RenderDoc or each of these specific shaders, check out our documentation in the Developer Tools section on our website. Another important factor that can affect your app's performance is the presence of Vulcan validation errors. Now, RenderDoc can enumerate these errors when opening a Vulcan capture. Simply enable API validation on replay when opening your capture, and a list of Vulcan validation errors will be listed in the Errors and Warning panel. But if you want to check for Vulcan errors over the span of an entire program execution instead of a single frame, then you use the Vulcan validation layer via setprop. Simply use the adb command shown here. You have to replace your app's package name in place of the bolded package name. After entering this command, simply launch your app. The errors or warnings will be shown in Logcat. You can use the tag validation to filter for the Logcat output. Did you know that you can also use RenderDoc to debug and profile WebXR applications on the MetaQuest browser? RenderDoc support came back recently on OS Update v46. So you can now launch the browser from RenderDoc and make captures of your WebXR application. Before we begin, we need to enable RenderDoc support in the browser. Put on your headset and enter Chrome://flags in the MetaQuest browser's address bar. Then search for RenderDoc Immersive Mode support and change the selection to Enabled. Then click on Relaunch for the change to take effect. Back to the RenderDoc client's Launch Application panel, toggle Show Hidden Files and select com.oculus.browser for the package and default activity for the activity. Click on Launch and RenderDoc will launch the browser, and then you can load your URL for capture. After making a capture, you'll be able to debug and profile your WebXR capture like a native capture. That's all for today's tools update. Look, we know it's a lot, and that's because we have made huge investments in the Vulcan optimization and performance tooling, and more is yet to come. We hope you leverage the optimizations we have presented today and use the tools we have demonstrated to verify your performance improvements, because together we can create compelling and performant experiences and help build a better metaverse. To learn more about everything we have talked about today, please check out these links. If you have questions, our developer forums can answer them. We'll see you next year.